Welcome to section 14.4. In this section, we're going to be using the information we got in the last section about calculating partial derivatives to find the equations of tangent planes to a surface and to do linear approximations. Linear approximations is something that you study back in Calc 1, but of course only in the xy plane with a line on a curve. In this section, we'll be looking at linear approximations using planes and surfaces. So to start off, suppose that f has continuous partial derivatives. An equation of the tangent plane to the surface z, which is f of xy, at the point P, which is x naught, y naught, z naught, is equal to z minus z naught equals fx of x naught, y naught times x minus x naught plus fy of x naught, y naught times y minus y naught. So this is the equation of a tangent plane. And you can see over here, I have a diagram of kind of what this looks like. So we've got our surface here, and we've got a plane that is touching the surface at this point right here. You can see it kind of sticking out right there. And we want to find the equation of this plane that touches the surface at that point. So what we do is we take the partial derivatives fx and fy. So you can see we've got these two tangent lines right here. Those tangent lines are created using fx and fy, right? They give us the slopes of those tangent lines. And we can use these to construct the equation of the plane. So, and you can see that this does mirror the equation of a plane a little bit, right? We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. It has kind of a similar form to it. So it is a planar equation, but it directly uses both of these partial derivatives. And you can see here the kind of the drop down of where these tangents appear on the surface. So you've got one that goes here and kind of tucks in back that way, and then the other one goes right there. So we can find the equation of the tangent plane simply by knowing the point that it intersects and by knowing the partial derivatives of the surface. So let's take a look at an example. So find the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. So we need a couple of partial derivatives. So we're going to get fx of xy. So partial derivative with respect to x. That's going to give us a 4x and a 0. So just 4x. Fy gives us 0 and 2y. It's our partial with respect to y. So our partial derivatives at the point 1, 1, 3, so we get fx of 1, 1, which is just 4, and fy of 1, 1, which is just 2. So our planar equation will be z minus 3, so that's that 3 right there, equals 4 times x minus 1 plus 2 times times y minus 1. And when it comes to setting up the equation, we could put this in standard form for the equation of a plane. So if we distribute the 4 out, distribute the 2 out, and then rearrange to put all of the variables on one side, so we would get 4x plus 2y, we could subtract the z over, so minus z equals, that would be negative 4 and negative 2 is negative 6. And then add it over, gives us a 3. So this would be the equation of the plane in standard form. Now, when it comes to using the tangent plane, we also could write this in more of a functional form because we're looking at the surfaces, like z is a function of x and y. So sometimes we'll also see planar equations written in the form z equals, so that if we plug in specific values of x and y, we can work with it more easily as a function. So I'll add the 3 over, okay, so basically keep the z by itself, and it gives us 4x plus 2y minus 3. So both are equivalent. We just have, again, the standard form of the equation and then the functional form of the equation. Now, I want to look just very quickly here right below this. What we're going to be able to use the tangent plane for is we want to be able to use it to make approximations for a surface. So we know that the tangent plane hits the surface at this point right here. But what if I want to find the value on the surface that's back here somewhere? Say like back through that way. But for some reason I can't. Maybe the surface is too complicated, maybe like just the function doesn't work very well, or the value itself is like too small of a decimal, whatever the reason may be. Instead of using the surface, we could instead look at the corresponding point on the plane and use that to estimate the actual value on the surface. So we'll see, of course, more examples with this, but for this one, for example, if we look at the point 1.1 comma 1.1, so really close to the point 1, here, okay? If we substitute this point into the plane, we get z equals 4 times 1.1 plus 2 times 1.1 minus 3. So that's going to be 6.6 minus 3, so that's 3.6. So this is the value of that point on the plane. Now on the actual surface, this one is a little bit easier, so this one doesn't take a lot of work for us to get the actual value. If we do, so 2 times 1.1 squared plus 1.1 squared. This will be 1.21, and then so it's 2.42, and then this is 1.21, which adds up to 3.63. So the actual value at the point 1.1, 1.1 on this paraboloid, the actual value is 3.63 down there. Now, if for some reason we weren't able to work with the paraboloid, if we couldn't find that value or it's too complicated or whatever, instead we could find 1.1, 1.1 on the plane and get out a value of 3.6, which if you're only rounding to one decimal place is exactly the same, right? It rounds the same way. So this would be a good approximation for us to use if we needed that, okay? So we'll see that, as long as we stay close enough to this starting point, the one that went into our equation, we can get pretty good approximations of surface values using a tangent plane. Of course, if we move too far away, like if I want to estimate, like a point over here with this tangent plane, that's not a good idea. We're going to be really far away from the value. But as long as we stay close enough to that point where we're starting, we can get very good approximations using tangent planes and much more simply than we could on the actual surface. So this is kind of explained in this next section right here. So linear approximations. In the first example, we found the equation of the tangent plane at the point 1, 1, 3. As we get closer to the value of the point, the function gives us a better approximation given by L of xy equals 4x plus 2y minus 3. We'll talk about what the L is about in just a second. So, but this is a good approximation to f of xy when xy is near the point 1, 1. So as long as we are near 1, 1, then this formula that we found for the tangent plane, right, it's the same one that was up here, is a good approximation of the actual surface. Now the function L, why we relabel this as L of xy, L is called the linearization of f at the point 1, 1. And f of xy equals 4x plus 2y minus 3 is called the linear approximation of f at the point 1, 1. So it looks like kind of a semantic difference where you have this and this. They look like they're just the same thing. If we look at them down here, so let me just rewrite these for general formulas here. So the linearization of a function f at a point AB, that'll be L of xy equals f of AB plus fx at AB times x minus a plus fy at AB times y minus b. Which, if you relate this back to our tangent plane formula, this part is this part, right? It's exactly the same. And basically, we just took this starting z value, that output value, and added it to the other side. And that gave us this. That's the f of AB. So this is the same equation as the tangent plane equation, just using some different variables, slightly different notation and terminology. Now, the linear approximation of f, this is denoted f of xy is approximately equal to f of AB plus fx of AB times x minus a plus fy of AB times y minus b. Now, the first thing that people usually ask at this point, these are the same thing, right? They're exactly the same formula, so why give them different names and why give them different labels? Well, basically, the linearization, this is the value on the tangent plane that we are getting. F of xy, this is the value on the surface that is being approximated using the tangent plane equation. Okay, so they do give the same thing. Okay, we're talking about the same stuff, but L of xy, this is how we would write it if we were just talking about the value on the tangent plane. Say this is the linearization of the tangent plane. So this is like the formula for it. And then this one is the point itself that we're trying to approximate with the tangent plane. So this one is more about the formula. This one is more about the point, about the end result that we get out of that. So if we look at top of the next page, we have another way of kind of looking at these linear approximations. A little bit of kind of back work here. If fx and fy exist near AB and are continuous at AB, then f is differentiable at AB. Differentiable just meaning we are able to take a derivative, okay? Or in this case, a partial derivative. So another way of looking at the tangent plane equation and at linear approximations is through the concept of differentials. And again, this is something that you would see a little bit in Calc 1, but only in 2D. Now we're looking in 3D. So in one variable, for y equals f of x, we said dy equals f prime of x dx. So this was kind of one of those like shortcut tricks where you're like, oh yeah, dy dx equals f prime of x. And so we just kind of imagine multiplying this across to the other side. And that's kind of the shortcut that they teach for differentials. So, but this gives us a definitive relationship between the derivative, f prime of x, and dx and dy. Dx and dy are going to be representative of changing in values for x and for y. So for a differentiable function of two variables, z equals f of xy, we define the differentials dx and dy to be independent variables. That is, they can be given different values. So like in the previous cases with just 2D, dx was independent and then dy directly resulted as whatever this was. So it was dependent on dx. Here, x and y are independent variables, so both dx and dy are independent. So we can change x and change y, and they will not affect each other. What they will affect, though, is the differential dz. So dz is equal to fx of xy dx plus fy of xy dy. So you can see similar formula to the one up here, right? If we just look at them one by one, they have that general form of derivative times dx, derivative times dy. And this gives us dz. dz is dependent on dx and dy, okay? So if we change the x value slightly and change the y value slightly, the new point that we get will have a different z value. So the z will change also. Now, if we take dx to be equal to delta x, so delta x is just the change in x on the function, so that's x minus a. Take dy to be delta y, which is y minus b. The differential of z, if we're kind of putting it in a new form here, dz equals fx of ab times x minus a plus fy of ab times y minus b. So again, we've kind of restructured this a little bit. So dx, again, that's the change in x. That's what delta x means. It's the change in x, which is x minus a, okay, for a starting point a. And then dy is the change in y, which is y minus b. So we get this formula, which again is that same formulaic idea as the linear approximation, the linearization, the equation of the tangent plane, all of that stuff. We're still talking about the same thing, just in slightly different ways. So the linear approximation, if we go back here, so this linear approximation, this whole part is just the dz from this equation we just did. So that's this whole part. So the linear approximation can be written as f of xy is approximately equal to f of ab plus dz. So picture kind of what this means here. F of ab, this is the function value at the point, the starting point. Okay, so AB is like our starting point. DZ is the change in Z along the plane, not along the surface, along the plane. So we started, at an output of 3, and we went up on the plane by, 0.5. So now our new output is approximately 3.5, something like that. And we will see an example with this in just a minute. But first, I want to look at a diagram that hopefully will make this a little bit clearer. So up here, we have the surface in blue. We have the tangent plane in orange right here. And then I have this big box down here is just to show where the guiding lines are so we can kind of follow along. So this is our starting point, AB, right? AB comma f of AB right here. So AB 0 and we go up. We want to get the value of this point up here. Okay, and that's this value right here. That's a plus delta x plus a plus delta x comma b plus delta y comma f of that. Okay, so we moved the x value a little bit, we moved the y value a little bit, and then we get a new z value that goes along with it. Okay, and you can see down here delta x, we change it this much. Delta y, we change it this much. Okay, by changing both of those, that puts us here, which puts us at this point right there. And we're trying to figure out what the output is of this point. Now, if we use the function itself, we can find the change in the function using delta z. So delta z is the actual change in the value of the function. So you can see right here, this is the original starting height right here, and we go up this high to get to the new one. That change from here to here, so here to here, is delta z. But if for some reason we cannot find the actual value on the surface, we can use the tangent plane. So the tangent plane, it's not going to get all the way to the actual point, but it comes right here. So we get an approximation. Okay, again, not exact, but it can be a fairly close approximation. This change in height is called dz. So this is dz, that formula that we've been looking at. So we're using dz to approximate delta z, okay, to get the change, the actual change in the function. If we can't get the actual change, we get the approximate change. Okay, so we go from here up to here. And then again, depending on the scale, it might be close enough for us. But that would be a different determination to make. Okay, so this is kind of what's going on with the differentials and with the linear approximation, right? Tangent plane, all that stuff. We're using the tangent plane to identify points near our starting point that approximate the actual surface values. So let's go ahead and take a look at an example. Given the function x squared plus 3xy minus y squared, find the differential dz, so that's the change in height on the plane. And then if x changes from 2 to 2.05 and y goes from 3 to 2.96, compare the values of delta z and dz. So we're going to see how close of an approximation we can actually get. So for part A, we have dz. So we're going to get fx of xy dx plus fy of xy dy so we need to take a couple partial derivatives of this. So that's going to be 2x plus 3y dx plus 3x minus 2y dy. So this is our formula for dz, okay, for the differential. So now, let's go ahead and figure out how accurate this will give us for an approximation. So let's see. X changes from 2 to 2.05. So that means when x is 2, dx is the change in x. Dx is not 2.05. It's the change in x from here to here. So the dx value will just be 0.05. And y is 3 with dy, again, not being 2.96, and also not just being 0.04, but being negative 0.04, because the value went down. So negative 0.04. So we just got the formula for dz, so let's go ahead and substitute that in right now. So we get 2 times 2 plus 3 times 3 times dx is 0.05 plus 3 times 2 minus 2 times 3 times negative 0.04, which that whole term will become 0. We get 4 plus 9, which is 13 times 0.05, which will give us 0.65. So we get dz is 0.65. Okay, so the change in function value from 2, 3 to the point 2.05 comma 2.96, the change in output is approximately 0.65. Okay, so it's 0.65 on the plane, not on the actual surface. If we look at the change on the actual surface, so we look for delta z, we're going to get the output at the new point, that's 2.05, minus f of, 2.05 comma 2.96, minus the output at the original point, which was f of 2, 3. Okay, so this will be new output minus old output will give us the change in output, okay, delta z, and this will be the exact change in output. So we need to run these points through the function. So for the first one, so we get 2.05 squared plus 3 times 2.05 times 2.96 minus 2.96 squared minus 2 squared plus 3 times 2 times 3 minus 3 squared. And already, this is looking like something that is not as easy to calculate as the one up here was. But we can get all of those numbers and calculate it out. We end up getting 0.6449. So delta z is 0.6449. So if we look at the values here, 0.65 is the approximate change. 0.6449 is the actual change. That's not that far off, right? If you cut it off at 1 decimal point, not round, but if you just cut it off, it's 0.6 both times. If you round this one, it rounds to 0.645, which then if you rounded it again would be 0.65, which is that value. So again, we're not saying that they're equal, but we're saying that in certain contexts, this could be just as useful as this, okay, or close enough to the actual value that we can go ahead and use this value instead. But this one is significantly easier to calculate. And the key here, obviously this example is not too rigorous because it's just kind of a 3-term polynomial here. The key difference is this one will never get more complicated, and this one will. Okay, so if we look at more and more complicated functions, this calculation gets worse and worse as the functions get bigger. This calculation will never change. It will always be a tangent plane. It'll always be fx, fy, plug in the numbers, and then dx and dy. Okay, so the tangent plane approximation or the linear approximation is satisfactory as long as we stay close enough to the starting point, and it's going to be much easier to compute. So dz is approximately equal to delta z, but dz is simpler to compute, even when the functions get tougher. Okay, so this is how we can use calculus and multivariable calculus to be able to approximate values on a surface when maybe we can't find an exact value directly, or the approximate value is sufficient. But that would be the end of section 14.4. That is our discussion on tangent planes and linear approximations and differentials. So I'll talk to you all in the next section.